In this video, we will introduce the notions of eigenvalues and eigenvectors of matrices. And let's begin with the definitions. And let's suppose that we start with an n by n square matrix A. Then the number lambda is called an eigenvalue of A if we can find a non-zero n times 1 column vector V such that A times B is equal to lambda times V. And this vector V is called an eigenvector of A corresponding to lambda. For example, it can be checked that this matrix times this vector is equal to twice the same vector. So this vector is an eigenvector of the matrix corresponding to the eigenvalue lambda equals to 2. So our first result gives us a way to determine the eigenvalues of a matrix. And it says that the number lambda is an eigenvalue of a matrix A if and only if the following determinant is equal to 0. And it is a determinant of the matrix lambda times the identity minus A. So let's see a proof of this result. And let us first assume that the determinant of lambda times I minus A is equal to 0. So what this means by our earlier theory is that we can actually find a non-trivial solution V of the following homogeneous linear equation. The equation lambda times I minus A times X is equal to 0. So there is such a non-trivial solution. But then lambda I minus A times V is equal to 0. And once we multiply, we have lambda times V minus A times V is equal to 0, which gives that A times V is equal to lambda times V. And since V is a non-trivial solution, so V is non-equal to 0, then V is an eigenvector of A with eigenvalue lambda. So lambda is indeed an eigenvalue. Conversely, let's assume that lambda is an eigenvalue of A. So we can find a non-zero vector V such that A times V is equal to lambda times V. But then we can rewrite this as lambda times identity minus A times V. This is equal to lambda times V minus A times V, which is 0. So V is a non-trivial solution of this equation. And this means that the determinant of this matrix is equal to 0. Again, by the previous theory that we have developed. An immediate corollary of this result is that a square matrix A is invertible if and only if 0 is not an eigenvalue of A. So let's see why this is true. To start with, we know that A is invertible if and only if its determinant is not equal to 0. But from the previous result, we know that 0 is an eigenvalue of A if and only if the determinant of 0 times the identity matrix minus A is equal to 0. But the determinant of 0 times the identity matrix minus A is equal to the determinant of minus A, which is equal to minus 1 to the n times the determinant of A, if A is an n times n square matrix. So we know that A is invertible if and only if its determinant is non-zero. And we know that 0 is an eigenvalue if and only if the determinant of A is 0. So the theorem follows. The matrix is invertible if and only if 0 is not an eigenvalue. And as a remark, in the tutorial sheet, you'll find a more elementary proof of the fact that if 0 is an eigenvalue of A, then A is not invertible. And by more elementary, I mean a proof not using the fact that A is invertible if and only if the determinant of A is not equal to 0. Let us now proceed to see a few examples. Our first example asks to determine all eigenvalues and all eigenvectors of the following matrix. And our first step to determine the eigenvalues is to solve the equation, the determinant of lambda times the identity minus A being equal to 0. Okay, so we compute this determinant. So lambda times I minus A is, so everything in the diagonal becomes lambda minus 1, lambda minus 4, and all other entries change signs because we have minus A. And now we just compute the determinant and factorize the expression that we find, and we determine that the actual answer is lambda minus 2 times lambda minus 3. And so this gives that lambda is an eigenvalue of A if and only if this expression is equal to 0, which happens if and only if either lambda is equal to 2 or lambda is equal to 3. Okay, so the exercise actually asks for both eigenvalues and eigenvectors. So we now proceed to find the eigenvectors. And we start with the eigenvectors corresponding to lambda equals to 2. These are all the non-zero solutions to the equation ax is equal to 2x. Equivalently, this is the same as asking that 2 times the identity minus ax is equal to 0. But twice the identity minus a, remember what a is equal to this matrix, so we are looking for the solutions of this system of linear equations. But we can immediately observe what the solutions are because both of these give the same equation, and if y is equal to t, then this gives x being equal to minus 2t, just by inspection. And of course, we need t not equal to 0 because we say that eigenvectors are non-zero. And similarly for lambda equals to 3, we solve the 3i minus a times x is equal to 0. We get these two equations, they are the same, and we get the eigenvectors minus t for t not equal to 0. Okay, as a remark, when we start with a 2x2 matrix A, and we know that it has eigenvalue lambda, it will always be the case that one of the rows of lambda times I minus a will be a multiple of the other row. So exactly what happened here. So this row was minus 1 times this row was minus 1/2 times, or minus 1 over 2 times this row. This will always be the case. And so we will be able to immediately write down the eigenvectors just by inspection. And this is to be expected, because the eigenvector corresponding to lambda is a non-trivial solution of the equation lambda I minus a times x is equal to 0. But then, if this equation has no trivial solutions, then this means that the rank of this matrix is less than 2. And in 2x2 case, this can only happen if one row is a multiple of the other. Now, if in the case A has order greater or equal to 3, then this will not be the case anymore. But what we can do, we can proceed with Gaussian elimination to solve the system that we want to solve. So suppose now that we have an n by n matrix A, then this determinant of lambda times I minus a will always be a monic polynomial in lambda of degree n. And this polynomial is called the characteristic polynomial of A. And we usually denote it by chi a of lambda. And in particular, by the fundamental theorem of algebra, we can write that chi a of lambda is equal to lambda times lambda 1 to the power of r1, lambda minus lambda 2 to the power of r2, times times lambda minus lambda k to the power of rk, for some distinct complex numbers, lambda 1 up to lambda k, and some positive integers r1 up to rk. So always the characteristic polynomial will be of this form. So this was the case before, when we found that the characteristic polynomial was lambda minus 2, lambda minus 3. So in particular, lambda is going to be an eigenvalue of A if and only if chi a of lambda is equal to 0. So if and only if lambda is equal to lambda I for some of the I from 1 up to k. And this positive integer Ri is called the algebraic multiplicity of the eigenvalue lambda I. So let's see another example. Okay, so in particular, over the complex numbers, an n by n matrix is going to have exactly n eigenvalues if we count multiplicity. So this should have been eigenvalues, not roots. So the characteristic polynomial has exactly n roots counting multiplicities, and so the matrix has exactly n eigenvalues counting multiplicities. Okay, so let's see another example. We are asked to determine the eigenvalues and eigenvectors of this matrix here. And we start by solving the characteristic equation. to find the roots of the characteristic equation. We do our usual process. We may need to do some row operations, and we proceed with row operations to determine the characteristic polynomial. And we found that it's lambda minus 1 squared times lambda plus 2. And what this means is that A has eigenvalues lambda equals 1 with multiplicity 2 and lambda equals minus 2. Our task now is to find the eigenvectors. And we will start with lambda equals minus 2, which is the eigenvalue of multiplicity 1. So we seek non-zero solutions to minus 2i minus a times x is equal to the 0 vector. So minus 2i minus a, we calculate it to be this matrix. So we are looking to solve this homogeneous system of linear equations. And because we cannot find the solutions by inspection, we proceed with Gaussian elimination. So after applying the Gaussian elimination as we were doing earlier, we find this matrix here, and we don't actually need to do the whole Gaussian elimination because now we can inspect the solutions. Because these two solutions are the same, we can pick z as we like, let's call it t. Then y must be equal to minus z, because minus 7y minus 7z is equal to 0. So y must be minus t. And then again, by back substitution, minus 2x minus y plus z is equal to 0. We plug in y equals minus t, z equals to t, and we get that x must also be equal to t. And of course, because we are looking for non-zero eigenvectors, non-zero vectors, then t must be different from 0. Okay, now let's proceed with the eigenvectors for lambda equals 1. And we seek non-zero solutions of I minus z and the identity minus a times x equal to 0. And we find this matrix, and now we just observe that this system of linear equations is essentially the system minus 5x minus 4y plus 4z is equal to 0. And we can immediately write down the solution. We can pick z as we like, we can pick y as we like, and then x is determined. And of course, because we are looking for non-zero vectors, this is for any s and t for which at least one of them is non-zero. Observe that in this particular case of lambda equals 1, which was an eigenvalue of multiplicity 2, we needed two free variables to describe the eigenvectors, and not just one. And in general, for eigenvectors of multiplicity 2, we may sometimes be able to describe them using only one variable, but sometimes we might need two. And this situation generalizes to eigenvalues of higher multiplicities. And in the language of vector spaces that we will meet soon, if an eigenvalue lambda of a matrix A has algebraic multiplicity m, for example, in the previous example, lambda equals 1 had algebraic multiplicity 2, then in this case, the set of vectors v such that AV is equal to lambda v will need at least two free variables to be described. And in the language of vector spaces, this says that it's going to be a vector space of dimension at most m. Now let's proceed with some new definitions. If we have a square matrix A, we say that it is upper triangular if all its entries below the main diagonal are equal to 0. So for example, this matrix is upper triangular because if we look at the main diagonal and we look at all entries below it, these three entries, then they are equal to 0. So it doesn't say anything whether, the entries in the main diagonal are allowed to be 0, are allowed to be non-zero. The entries above the main diagonal are allowed to be 0, are allowed to be non-zero. And lower triangular matrices are defined analogously. And by taking cofactor expansions and using induction, we can actually show that the determinant of a triangular matrix is equal to the product of its elements in the main diagonal. So here the determinant of A is 2 times 3 times 2, which is equal to 12. And since lambda times the identity minus A is also going to be a triangular matrix, lower or upper, whenever A is triangular, then we see that actually the eigenvalues of A are in fact exactly its diagonal entries. So in the above example, A is going to have eigenvalue 3 with multiplicity 1, and eigenvalue 2 with multiplicity 2. Suppose now that we have a matrix A, and suppose V is an eigenvector of A with eigenvalue lambda. So what this means, it means that A times V is equal to lambda times V. And so if we try to calculate A squared times V, this is by definition A times AV. But AV we know is equal to lambda times V. This is equal to lambda times AV. But AV is equal to lambda times V. So this is equal to lambda squared times V. But what this means, it means that V is an eigenvector of A square with eigenvalue lambda square. So more generally, if we are told that lambda is an eigenvalue of A, and we are given any polynomial P of X, then P of lambda is going to be an eigenvalue of P of A. And in fact, all eigenvalues of P of A arise in this way. So for example, we have already worked with this matrix, and we've seen that it has eigenvalues -2 and 1. So if we take P of X to be 2x cubed minus x plus 5, then P of A is 2a cubed minus a plus 5 times the identity. And this is going to have eigenvalues P of -2, which we can calculate to be equal to -9, and P of 1, which is equal to 6. And in fact, it's also the case that multiplicities are preserved. So -9 is going to have multiplicity 1, and 6 is going to have multiplicity 2.